yesterday we looked at how we can generate a symmetrical coupler curve. So, we looked at if M1 and M2 are two positions of the coupler curve, then we saw that. So, first I look at I show OB A1 equal to OB A2. Okay, I take symmetrical positions of the crank about the frame, and I show OB A1 equal to for the two positions of the coupler points. I show this. Then I show beta 1 equal to beta 2, this angle, these two angles are equal. Then from there I show OB M1 equal to OB M2. Okay. Once I show that, triangle M1 OB M2 is an isosceles triangle. Once I show that, therefore, the perpendicular bisector of M1 M2 will pass through OB and bisect that angle. Will pass through the opposite vertex and bisect that angle. And then we showed that gamma, the angle that bisector makes with the frame, is a constant. That means as the linkage moves, it does not, that line of symmetry does not change. Okay. M1 will always be reflected about that line, because that line does not change. So, with the other conditions of so you are choosing. So, our synthesis conditions were OBB equal to AB and also equal to MB, and MB would be at an angle, because the circle passes through all three points. M lies on that circle and makes an angle equal to twice the angle that the line of symmetry makes with the frame. Okay. So, angle ABM equal to B cap. Okay. So, this is how you synthesize a symmetrical coupler curve. Okay. Now, we will move on to one of the most interesting results in coupler curves, which is called the Roberts-Chebyshev theorem. So, if you remember, I took this diagram from your first tutorial. Okay, I gave you this mechanism. I did not tell you anything special about the links, and I asked you to find the mobility of this mechanism. Go ahead and do that now and tell me what the mobility of this is. No? What do you get? What is J1 equal to? -14? What is M? -1. That means it is an over constrained linkage. So, you would not expect it to move, right. Okay. But there is something special about this linkage with certain link lengths. So, if you look at these three, now this is a parallelogram, this is a parallelogram, this is a parallelogram. So, if the links form these three parallelograms, then you actually have a mobility of 1 for this mechanism, provided those links satisfy that, you know. So, links, these are parallelograms. So, here is another configuration. So, you see here you have one linkage like this, okay, and that has this coupler point, okay. You have another linkage, another 4 bar here, this as the coupler point, and then you have the red one, okay. This is the coupler point and this is the 4 bar. So, if you look here, these 3 4 bars are assembled such that these form these parallelograms, right. You have 1, 2, 3 parallelograms, okay, and you see what is happening here. So, it is moving and you can see that the point P traces the same curve in all 3, I mean point 3 traces one curve. So, these are just 4 bars. If I disconnect them, okay, I will again get single degree of freedom mechanisms, okay, and that coupler curve, that the curve that point P traces should be the same. I can disconnect the 3 linkages, make them separate 4 bars and my point. So, this is what Roberts-Chebyshev theorem states, that planar, there are 3 different planar 4 bar linkages which will trace identical coupler curves. So, if you have a particular coupler curve you want to trace, you can find 2 more linkages that will trace the same coupler curve, okay. Why is that significant? Because the space requirements of the other 2 linkages may be more suitable for your application, because the location of the other pivot, other fixed pivot may be more suitable for your particular. So, if you have designed or if you have picked a 4 bar which has a certain coupler curve, you can find 2 more 4 bars using this theorem that will generate the same coupler curve for that particular point P, okay. So, that is what this shows. So, I can have the red linkage. So, if I just have the blue linkage for instance, that point P is going to trace that coupler curve. Now, with a special construction I can determine the red and the purple linkages that will also generate that same coupler curve, okay. Okay. So, that is the Roberts-Chebyshev theorem. So, let us look at, So, I can separate it out. So, if this traces a curve, I have, let us see how we construct the other two linkages. So, if I have so this is my point P, which is the coupler point. So, here. So, let us start off with a 4 bar that generates a certain coupler curve, and that coupler curve is generated by this point M, which is located with respect to the base AB, and this is the coupler triangle. These are the angles that define the coupler triangle, because we will use that when we look at the construction. So, the first thing that you do, you have the original 4 bar, okay. Now, from OA you draw a line parallel to AM. Okay. And then a line parallel and equal to OA, okay, so to form this parallelogram. Okay. Now, using this base, okay, I construct a triangle that is similar to the coupler triangle ABM. Okay, I have to follow the same order of angles. So, if this, okay, from here I construct, this is the base I have, I construct at an angle alpha and an angle beta, that will give me this point C1. Okay. So, this order, so this is the coupler base AB. For this is the, with A1M I construct the same coupler triangle, similar triangle, it is not congruent, okay, because it depends on this base AM, which is actually equal to OAA here. Now, on the right hand side, okay, pick here I have OBB and BM. I first construct this parallelogram. This is parallel to this, this is parallel to this. Okay. Now, I use this as the base for my coupler MB2, okay, and I have to construct the same alpha from here, beta from here. The order is very important, the order which you construct the angles. Okay. If you mess up and say this is beta and that is alpha, you will not get the desired effect.
If you do that alpha beta swap for both the top two triangles, then it won't make a difference.
You go you try it out and see what will happen. You are saying swap for these two, try it out and see, because there is something. So, this, there is a particular condition for OC, right. I mean, you have to have OC as a fixed point when you construct it, right, and that. So, now look at finishing up. So, now I have MC2. So, from C1 OC2 I construct a parallel that will form the fourth link of my left cognate. So, the linkages that generate the same coupler curve are called cognates. So, for a particular 4 bar, I will have a here I call this the left cognate and the yellow one the right cognate. Okay. So, then this becomes parallel to this, and whatever point they intersect at is what I call my OC. Now, imagine OC is not a fixed pivot. Okay. Suppose OC is not a fixed pivot, then in my mobility equation, if OC is not a fixed pivot, my mobility equation becomes 3 into 10 minus 1 minus how many joints go away? One joint, the one between the fixed link and the. So, I will get 13 J1s and I end up with a mobility of 1. Okay. So, if I do not fix OC, I know that this linkage can move. Okay. For this so even if I have, regardless of any condition on the lengths of the links or the geometry, if I do not have OC as a fixed point, this linkage will move. Okay. So, what we will show is that for this particular geometry, OC stays stationary, which means I can use that as a fixed pivot, which means I can now split this into 3 4 bar linkages. Okay. So, without any conditions on the link lengths, if OC was not a fixed pivot, this would have a mobility of 1. This linkage would be fine if I just remove one of these fixed, if I do not fix one of the pivots. However, that point is going to move. What I am going to show is that for this specific geometry, that point OC, even if it is not fixed, it will essentially remain stationary as the linkage moves. That point OC will not move. So, if I can show that, then that means I can split this into 3 linkages at M. Then I can make OC a fixed pivot and split this linkage at M into 3 separate 4 bars, and all of them will have the same path for M, which means they are tracing the same coupler curve. Okay. So, here we have, it is basically just showing the split links I have. So, I can have, depending on my application, I can get a linkage that is more suitable in terms of size and location of one of the fixed pivots. So, I get 3, if I solve a path generation problem, I immediately have 2 more alternatives by constructing the cognates for that particular coupler curve. Okay, because for path generation, remember, scaling is not an option. For function generation, I can scale the linkage, I can play with that. For path generation, it is not an option. Okay. With path generation, I can get 2 other options by constructing the cognates for the 4 bar. So, this is the right cognate, same coupler curve. So, now we are going to show how this joint OC can be, does not move for this particular geometry, for this particular construction of the cognates. Okay. So, that is what we are going to show. Is the construction clear? Construction of the coordinates. Given a 4 bar, this is the construction of the coordinates. This is the important part, constructing this triangle such that it is similar with the angles in the same order. I mean, even if I switch the angle, it will still be, the angles have to be in the same order. Okay. Okay. So, now let us look at we will use complex numbers to show this. So, if I denote this by, I say the vector z is OA, OC, e power I delta. So, here it is broken here, but essentially think of z as the vector of length OA, OC. With respect, I am taking the coordinate system with the x aligned with the frame just for simplicity, and if that makes an angle delta, then the vector defining point OC. Is OA, OC, e power I delta. If I can show that both the length and the orientation of this vector do not change as the linkage moves, then I will have, then it means OC is a stationary point, right. So, I have to show that this is equal to a constant. Okay. So, what we will do is, we will express this vector in terms of the dimensions of the original linkage. So, I have OA, AB, OB, okay, is my original linkage, and I need to, and M of course. So, that is my original 4 bar. I want to express the this distance in terms of the parameters of the original linkage, and they have to be, when I do that, ultimately I want something that is independent of the angles phi 2, phi 3, etc., because those are the ones that are going to change as the linkage moves. Okay, phi 1, phi 2, phi 3, that is the notation that is used here. It should be independent of those 3 angles, which are the angles of the 4 bar, our usual theta 2, theta 3, theta 4, here they go. Okay. So, if it is independent, which means as the linkage moves, if this vector remains constant, then you have established that I might as well make it a fixed pivot. Okay. I can make that a fixed pivot without any issues. Okay. So, let us look at this vector z. I can write this as z equal to OA A1, okay, e power, this angle is phi 1, okay, and it is parallel to AM. Okay. So, the angle with respect to the positive x of that is alpha plus, yeah. So, this is e power I phi 2 plus alpha, that is the angle with the x axis, plus A1 C1, what is its angle? You can see here with respect to the x, its angle is phi 1 plus alpha. And then plus C1 OC e power I, it is phi 3 plus alpha, because it is parallel to MC2. All the angles are measured positive counterclockwise from the x axis, from the positive x axis, which is taken along the frame in this case. So, this angle, the angle of MC2 with respect to the x axis is phi 3 plus alpha, this angle here, this is phi 3 plus alpha. Okay, because in this case OA1 is parallel to AM, and here C1 is parallel to MC2. So, because of the parallelograms and the similar triangles, I have the following in terms of the original linkage. I want to express everything in terms of the original linkage. OAA1 is equal to AM. Okay. I want to take anything that is not in terms of the original linkage and express it in terms of that. If I look at these similar triangles, the coupler triangle, A1 C1 by, this is alpha, this is beta, this is gamma. Okay. So, I have A1 C1 by A1M will be equal to what? AM by AB in terms of the original triangle, because they are similar triangles. Therefore, A1 C1 equal to A1M into AM by AB. Now, again A1M is equal to OAA. Therefore, A1 C1 I can write it as AM by AB okay. So, I can basically substitute that into this. Let us just, then A1 C1 is completely in terms of the original 4 bar. Then for the third I have C1 OC, okay, M C2 is equal to C1 OC. Let us say C1 OC is equal to M C2. Okay. In this, again comparing it to this triangle, M C2 by M B2 is equal to A M by A B. And again M B2 is equal to O B B. Therefore, C1 OC equal to M C2 is equal to A M by A B into O B B. Okay. This is what I have. I have shown that A1 C1 equal to OAA into AM by AB. And C1 OC is equal to OBB into AM by AB. Okay. Sorry, here this, yeah. And OA A1 equals AM, right. So, I can also write this as AB into AM by AB. So, my Z, I can now remove what out of the equation? All of them have AM by AB, right. AM by AB e power I alpha, I can get that out, and I have for OAA1 I have AB e power I phi 2 plus, for this one I have OAA e power I phi 1 plus, for this one I have OBB e power I phi 3. Okay, I can just rearrange that and write it as right. If I start from here, I have OAA e power I phi 1. I am just rearranging those terms, plus AB e power I phi 2 plus OBB e power I phi 3. What is this equal to? It is nothing but from your loop closure, this plus this plus this is equal to this. Okay, it is just the length OA OB, because I have taken x along that, the angle of that is 0, right. So, I get this is equal to AM by AB into OA OB e power I alpha. All these lengths are constant, AM, AB, OA, OB are constant. So, my AOC is equal to AM by AB into OAOB, which is equal to a constant, and my delta equal to the angle that Z makes is equal to alpha, which is also a constant. So, that means that point OC can be taken as a point on the fixed link, because it remains stationary for this particular geometry. Even if I do not have that as a fixed pivot there, for this particular geometry, that point will not move, because its location as this linkage moves remains the same. Okay. So, this is a geometric proof of why these 3 linkages, why these other 2 linkages will also generate the same coupler curve. Okay. So, this tells you now that you have, okay, one more thing. If you look here, it says OA OC equal to AM by AB into OA OB. So, from here OA OC by OA OB equal to AM by AB. That tells me that the triangle formed by the 3 fixed pivots is similar to the coupler triangle. I have already shown this angle is alpha. Okay. So, this will be beta, this will be gamma. So, you locate the third fixed pivot by constructing a triangle with base OA OB that is similar to the coupler point whose motion you want to find. Okay. So, this is how you get the location of the third pivot. So, if you have the original 4 bar, you can find the location of, and if that is more suitable, then you can look at using one of the coordinates. If OA OB, one of those is not suitable, then you could get an alternative 4 bar which has OC as one of the fixed pivots. Okay.
How did we get that in the first place, that OAOC is equal to OAM by AB?
From here, OAOC I showed here, right. Z, this I took it as the distance OAOC e power I delta. Okay. So, here I found that the length OAOC equals this. Okay. a simpler construction. So, now you can find OC. Oh, one more thing. So, if because of this construction the velocities are also, so if your original linkage, you know, if omega 2 is your input link, okay, now the velocities of these three linkages are also related, right, because of the, you can think of each of these as a, because these form parallelograms, right. So, if this is omega 2, omega 2 will be the same as omega 9, right. So, this is omega 9 and that will be the same as, this is parallel to this omega 7. Okay. So, how you, so if the speed at which you are traversing the coupler curve is important, then you have to know which one, you know, when you change the linkage, what you give as input also will matter. Okay. So, there are velocity relationships based on these parallelograms between the various links, and therefore, you will use that to determine how you drive the linkage. Cayley came up with, so you can locate OC from Roberts-Chebyshev theorem, right, by just constructing the triangle that is similar to the coupler triangle. So, the location of OC is immediately determined. Cayley came up with a different method for determining the link lengths of the other two linkages. So, instead of doing the parallelogram, you know, the construction, this is a simpler construction to determine the link lengths. So, you think about this original linkage which was like this, okay. Imagine that you disconnect it from here and you straighten it out. Similarly, here disconnect it from the fixed pivot for the purposes of construction and you straighten it out. So, that is OA, that is this configuration here. What you see here is you have the coupler triangle and you have the linkage disconnected from its fixed pivots and flattened out, so that it is flattened out with respect to the base of the coupler, and then you just construct lines parallel. This is not the actual location of OC, you have to be very clear about that. This only gives you the link lengths for the other two, but from here I can get the link lengths OA A1, C1 OC, C1 A1. Okay, from this construction, from Cayley's construction I get the link lengths of the other two cognates. So, one will be this, okay, and this will be the coupler. So, the link lengths you get from this construction, but the actual location of OC you get by constructing a triangle that is similar to ABM with OA-OB as the base, because this is not the, these are not the actual locations of OA-OB. Although this triangle is also similar to the coupler triangle, OA, these are not the actual locations of OA-OB. OA-OB are somewhere here, okay, somewhere out there. Okay. So, you cannot use that for the location of OC. Find the location of OC by constructing a triangle similar to AMB with actual OA-OB as the base. So, you can use this. So, suppose you have a coupler point that is not away from the coupler base, say it is on the coupler base, right. Essentially this whole thing collapses now. You do not, so M is not, M is on AB, okay. So, it is like this whole triangle just flattens out, right. You can still use the, I will show you an example tomorrow. You can still use the similarity, the ratio in which M divides AB, you can use that to construct the coordinates for that.